Chapter 5, Section 4, Medians and Altitudes. The median of a triangle is the segment whose endpoints are a vertex, and the other one is the midpoint of the side opposite the vertex. So if we're looking at vertex F, this is one endpoint, and the other endpoint is the midpoint of this side, which is opposite the vertex. The concurrency of medians theorem says that the medians of a triangle are concurrent at a point that is 2/3 the distance from each vertex to the midpoint of the other side. So from this we can see that DC is 2/3 of DJ. So DC is 2/3 of the length of the whole median DJ. Now the point starting from the vertex to that point of concurrency is the longer point, whereas the point from the midpoint is the shorter. So they're in a ratio of 2 to 1. DC is twice the length of CJ. The point of concurrency of the medians of a triangle is called the centroid, or the center of gravity, and it's always inside of the triangle. It's never on the triangle, it's never outside of the triangle. The only one that can be on or outside so far is the perpendicular bisector. The altitude of a triangle is the perpendicular segment from a vertex of a triangle to the line containing the opposite side. The altitude can be inside or outside of the triangle. It just has to be perpendicular to the opposite segment. So the lines that contain the altitudes of a triangle are also concurrent. The lines that contain the altitudes of a triangle are concurrent at the orthocenter, so that's what this point is called. The orthocenter of a triangle can be inside, on, or outside of the triangle. So now a perpendicular bisector, they meet inside, on, or outside the triangle, and the altitudes meet inside, on, or outside of the triangle, but the altitudes meet at the orthocenter. In an acute triangle, you can see they're meeting inside. Notice that it goes from the vertex and it's perpendicular to the base. It's not a perpendicular bisector. It's an altitude because you're talking about the height of the triangle, just like what we use to find the area. In a right triangle, we can see that they're meeting on the triangle. And in an obtuse triangle, you can see they're meeting outside of the triangle. But each time where they're concurrent, that point of concurrency is called the orthocenter. Now, this question is asking what are the coordinates of the orthocenter of DEF? Well, we can see a few things here. The orthocenter are where the altitudes meet. Well, the altitude from point E to the opposite side DF is a vertical line that's perpendicular to the horizontal base. Now the other ones are going to be a little bit more challenging. We need to find a line that's perpendicular, let's say, to EF from point D. So we need to find the slope of EF, find the line that's perpendicular to it through this point. So we're going to use the point slope formula. So we have EF. You can see that from this point to this point, you're going down 2, so -2, and right 1. So the slope of EF is -2/1. So perpendicular to it, I should say the slope equals -2. Perpendicular slope would be +1/2. And the point we want it to go through is D, and the coordinates for D are 3, -2. So using the point slope formula, we plug in our y1, which was -2, and minus and -2 means +2, equals the new slope times x minus x1, which was 3. This tells us that the equation of that line, subtract the 2, would be y equals 1/2 x 7/2, minus 7/2. So y equals 1/2 x minus 7/2. is the equation of the line from D to here that's perpendicular. Now you only need to find 2 of the altitudes in order to see where they're going to meet, because the third one's going to meet in the same place. So now we can see that this slope from point D would be going up 1, right 2. So it's meeting this line at this point, and that point is 5, -1. So this is the orthocenter. You can also use a system of equations to do elimination or substitution. So in this case, the equation of line EF would be x equals 5. You'd plug in the 5 here. So 5 times 1/2 is 5/2. You'd get 5/2 minus 7/2, which would give you -2/2, which is -1, and that's our y value. And then you'd plug in that -1 and solve for x. So you'd plug in -1 here, then add 7/2 to the other side, multiply both sides by 2, and you'd get the 5. Sometimes you can see it on the graph, but it's always best to use algebra, plug it into the system, and make sure. So just to sum up everything that we've talked about so far, perpendicular bisectors meet at the circumcenter. Perpendicular bisectors can meet inside, on, or outside of the triangle, depending on what type of triangle they are. It's called the circumcenter because there is a circle that you can circumscribe about the triangle, because that circumcenter is equidistant from all of the vertices. So that creates a circle that you can circumscribe about the triangle. The incenters where the angle bisectors meet, that's always going to be inside of the triangle. It's equidistant from all of the sides, but we're talking about distance, so it has to be the perpendicular distance from all of the sides. And you can inscribe a circle inside where the center is the incenter. The medians also always meet inside of the circle at the point called the centroid. The medians, we know, go from one vertex to the midpoint of the other side. And the altitudes meet at the orthocenter, and that's either going to be inside, on, or outside of the triangle. So the perpendicular bisectors and the altitudes are the only ones that can meet inside, on, or outside of the triangle. Angle bisectors and medians have to meet inside of the triangle.